looking at the example we have right now, it said, which of the following could represent our slope field? So one of the things I look at or notice is that the slopes here are negative, whereas the slopes here are positive. So one of the things you could do is take a point from maybe this area here, which is -2, 2. So at -2, 2, we're looking for a positive slope. So if you take that -2 and plug it in for x, and plug 2 in for y, what happens in example A? Yeah, so is that a 0 on that graph? No. So it can't be A. Same thing for B, you have -2 minus a 2. So I get a -4. Is my slope at that point negative? Can't be B. Here we have a negative. That becomes 2. 2 plus 2 is. Okay, so now C is a potential choice. And then similarly in D, you have -2 squared, which is 4. 4 minus 2 is 2. So now I have to be like, okay, well, now I need a different point to help me try to figure that out. So maybe I go over here and I go to +2, +2. And I pick that point because the slope at that point is, yeah. So now if I pick 2, 2, it works for C, but not for D. And again, you could have started with the point 2, 2. Like, you want to just pick a slope that you know is going to get you a number that you can kind of recognize, whether it's positive or negative. And then I try to pick numbers that are easier to plug in. So we're only going to do one of the differential equation examples. I feel like we did a lot of them yesterday with like the slope fields, but I also feel like this one is kind of like more along those lines of like those gross problems that popped up on some of the more difficult slope fields yesterday. So we have given the differential equation x squared plus 4 dy dx equals xy. Find the particular solution when you have initial condition 2, -3. So I like to manipulate my equation and say, okay, well, if I divide by y, I have 1 over y dy. And then I'm going to multiply by dx. But that still leaves this x squared plus 4. So that x squared plus 4 is currently being multiplied, so we have to divide it to the other side. So I have 1 over y dy equals x over x squared plus 4 dx. When the degree of the top variable is 1 more than the degree of the bottom variable, we need to use sum. So we get 1 over y dy, and we're going to integrate 1 over u du, and we're also going to integrate 1 over y dy. So what do we know about the antiderivative of 1 over anything? It becomes an ln. So I have ln of y equals 1/2 the natural log of x squared plus 4 plus c. At this point, I'm probably going to solve for my c value. Because that 1/2 in front of the ln kind of makes it gross and cutesy. So I'm going to plug in those initial conditions to find my c. So that's going to now replace the c in my problem with all those outlets. There's the only way to like really kind of clean it up is to bring those 1/2s like in as a power. The only reason you would do that is because we're going to e both sides to like get the y alone. And that'll like kind of help you see it, but this becomes ln y like all up above. But you have to remember that like e to something all up above being added is really like that e to all of those things being multiplied. So just because my space is a little bit limited, all these plus signs, are kind of like multiplication of that variable. That negative actually drops that one, which is why I was hesitating about the trouble. It's going to drop that one to division. So the e's and the ln's will go away. So here, we get y. Over there, you get 1/2 ln x squared plus 4 times ln 2. So it's really like the natural log of 2 over 2 x squared plus 4. And I told you the subtraction became division. So down below, you'd have 1/2 ln 13. What do you know about a half divided by a half? They're going to go away. Oh my goodness, my ln is here also. The e and the ln of 2. And my e. So it comes up rather nicely, but a lot of effort. More than likely, this will be like an open-ended kind of question.